Hey everybody, welcome back. I'm really excited today because we're going to be talking about one of the most popularly used families of methods to solve reinforcement learning problems out in the real world. And in doing so, we're going to be tackling one of the, if not the most popular fundamental theorems of reinforcement learning, the policy gradient theorem. Now we're going to demystify what all those words mean and tackle the importance behind them in due time. But to start with, and through this entire video, we're going to be tackling a very simple problem, which is going to help us understand the underlying methods that we're using. So we're going to assume this handsome fellow right here is you. And your job is simply to decide a binary choice each and every day. You're going to decide whether you want to order more or order less of a particular product every single day. So you can imagine you're the owner of a store that just sells a single product. And each day you just need to decide, I want to order more of this product for the next day, or I want to order less of this product for the next day. Now, we're going to be getting to this in a moment, but in the context of a reinforcement learning problem, this more or less decision is your actions, are the actions you're taking each and every day. Now, also in the context of a reinforcement learning problem, there are some states in the world which are going to impact the rewards that you're actually getting as a consequence of your actions. In our simple example, the state of the world is just a single variable p. And p measures the change in demand for this product that you're ordering more or less of every single day. We can assume that p is either positive, which means that there is more demand for this product than there was the previous day, or p is negative, where there is less demand for this product than there was the previous day. And we can enumerate the rewards you get as a function of the state of the world, p, and your actions, which is again ordering more or less, in this very, very simple tree structure right here. So if p is greater than 0, which means that there is more demand for this product than there was the previous day, then you should order more of it because people like this product and you should have more of it on your shelf. So in that case, on the left branch, if you order more of the product, you have a positive reward of 1 over p. However, in the opposite case where the demand is growing, but you mess up and basically order less of the product, then your reward should be negative. So it's negative 1 over p. In the opposite case altogether, where the demand is shrinking, the roles are basically reversed. You should get rewarded for ordering less of the product because people don't like it so much. And so in this very simple 2-column setup here, we have everything we need in the language of a reinforcement learning problem in order to get started and think about what it means to solve this problem. To recap, our states of the world are going to be just enumerated by this variable p, which is telling us the change in demand for the product. The actions, again, are simple binary decisions each and every day of whether to order more of this product or order less of this product. And the rewards are given by this binary tree structure that we've enumerated right here, which are a function of the states of the world, again p, and the actions we're taking, either ordering more or less. And now what I think is going to be really helpful for what's coming, and to help us kind of understand what depends on what in this reinforcement learning problem, I want to go ahead and fill out how the states, the actions, and the rewards at any given time step depend on those same quantities in the previous step in time. Because like any reinforcement learning problem, we're basically progressing through time. We are having some state initially, S naught, and there's some action we take as a result, A naught, and that's going to kind of kick off the process. That's going to determine the states we see next, which are going to determine the actions we see next, which are going to determine the rewards that we get next, and so on and so on. So I think it's really helpful for us to, in real time here, draw the arrows for what depends on what. So there's some initial state, which is not dependent on anything. That's just what we accept as given. But that initial state is going to impact the action that we take in the very first time period. And so that initial state, we're going to look at it, and we're going to say, based on that initial state, I'm going to decide some action, either ordering more or less of the product. Now we get to the next time step. The reward that we immediately see after that is going to be a function of the state that we were just at and the action that we just took. And so to see that clearly, we can go back to our tree structure. These rewards that we're seeing down here as the leaf nodes are going to be functions of the states we were just in and the action that we took as a result of those states. And so we can draw 2 arrows, one coming from the previous state and one coming from the previous action. Now, it's not just the reward here that's going to be influenced by the state and the action in the previous time step. It's also going to be those same exact 2 arrows that we draw in order to determine what the state is going to be in this next time step. So if we think about what's the state in the next time step, in this case, that's what is the change in demand for the product. What is that going to be dependent on? Well, it's going to be dependent on the change in demand for this product in the previous time step, more generally the state of the environment in the previous time step, and also going to be dependent on the action that we, as the agent, took in the previous time steps. That's going to be dependent on the action that we, as an agent, took in the previous time step. And so these are all the arrows we basically need to understand, because if I basically copy-paste these arrows for going from the first to the second time step, the second to the third time step, and so on, that's going to be the same exact arrow. So let's do one more example here to make sure we understand. Now we're existing in the second time step, where everything is subscripted by a 1. How do we draw the dependency arrows from this time to the next time step? Well, our action now is, again, only going to be a function of the state that we're seeing here. We're going to see that this becomes a very, very important structure that's going to help us simplify the solving of these problems considerably. And now we can draw these arrows accordingly as well. What's the reward look like in the next time step? That's going to be influenced by the state that we were just at and the action that we took as a result of that state. What does the state in the next time step look like? That's going to be dependent on the state previous and also the action that we just took here. And if there's one more arrow to draw here, then in the third time step, our action is again going to be just a function of the state we're looking at here. So if I had drawn all these arrows to start with, and I just tried to explain them to you, I think it would have been a lot more convoluted. But since we drew them together and we're talking about them in real time, hopefully now understand why each arrow is the way it is. And it's crucially this structure, it's crucially the substructures in this causal dependency graph that's going to let us simplify the solving, and is at the heart of these policy gradient methods in reinforcement learning. And a final thing I want to do before we go to the next page is define this whole set of states, actions, and rewards. So S0, A0, R1, S1, A1, so on, are collectively called a trajectory. And we're going to give that a overall name, a symbol of tau. Tau is going to be the set of all of the states, actions, and rewards that we are going through as a result of a particular policy that we choose. And it's exactly that policy which I would like to next define for you, and which is going to be important to understand what the heck a policy gradient method is. So now we're actually getting from the framework of setting up the problem to actually solving this problem. How do we, as this business owner, actually come up with some kind of framework for, based on the state I'm seeing in the world, which again is just the change in demand for this product since the previous day, how do I use that information to come up with some kind of smart way to decide whether to order more or less of the product? How do I know how to decide that rule? And so what we can do is say that, you know what, I'm going to pick my probability of ordering more product on the next day as a sigmoid, which is modeled by some parameter theta. And it's this parameter theta that we're going to learn. So we're going to learn this parameter theta times that p, times that change in demand for this product since the previous day. And so if I draw that in a picture, like we know with any sigmoid, we're able to input anything between negative infinity and positive infinity. And on the y-axis, it's either going to be bounded between 0 or 1. And so we decide to use exactly this rule to decide the probability that I'm going to order more of the product. For example, if we settle on some theta, which I haven't shown how exactly we're going to do that yet, and that's going to be the focus of the rest of this video, but let's say we found some way to pick a theta, and let's say p is some very negative number here, so there's not really a lot of demand, the demand is diminishing for this product. That's going to make our probability of ordering more of the product very, very small. On the other hand, if p is very large, people really want this product, then that's going to make the probability of ordering more of this product much closer to 1, which intuitively does make sense. And so this map between states and actions, because that's exactly what we've created here, even though this looks rather simple, it is basically a mapping between the state of the world, which is this p, again, in the language of our reinforcement learning problem we set up today. We're mapping the state of the world p to the action, or more clearly, the probability of taking a certain action in this current time step. And so this overall thing, this overall map between states and actions, is called our policy. And that is one of the key terms to understand today. in the language of reinforcement learning, a policy is some kind of rule for based on the state of the world I'm seeing. It doesn't have to be a logistic regression. It can be as simple as a logistic regression. It can be a decision tree. It can be an extremely complicated neural network. It can be something else altogether. It's just something that allows us to look at the state of the world and intelligently say, based on that state of the world, here is what I, the agent in this reinforcement learning problem, are going to do next. Here's my action in order to best have a strong reward in this time period. And so that's the policy. Now we switch into problem-solving mode. Now that we've understand the setup of this problem as a reinforcement learning problem, now that we've defined our policy and what form our policy is going to take for today, how do we find the ideal policy? And again, the only parameter that we care about here, for simplicity, in real life there will be lots of parameters, lots of different thetas that you want to vary, but for us there's just this one real number theta that we want to learn accurately. How do we find that ideal policy, or in other words, how do we find that ideal theta? Well, we can kind of fall back on other types of machine learning problems we've solved before. Like for example, if we were doing a supervised machine learning problem and we did have labels, then we might proceed as setting up some kind of loss function, and then we might try to take the derivative of that loss function with respect to the parameters that we're trying to learn and go in the direction of decreasing loss so that we're learning these ideal parameters. And so we can operate in a very similar way, except instead of a loss function here, which is something we'd want to minimize, we're going to set up a function j, which is a function of just that theta parameter that we're trying to learn. And that's going to be equal to the expected total reward if the policy that we chose to use was this logistic regression decision rule with that parameter theta. And so instead of minimizing that, we want to maximize it, since it's not a loss function, but it's some measure of the expected total reward. If we can find a theta that's going to maximize the expected total reward, then that in some sense should be a good theta to use as our policy, and we should be safe to use that policy in all subsequent days. So it's important to note at this point, what is this expected value actually over? Because anytime you see an expected value in a math problem, one of the things you want to ask is, well, an expected value is basically an average over a bunch of things, but what are the things here? So this expected value, and it's not immediately obvious, and it's important to state it explicitly here, is over all possible trajectories under the policy that we're talking about here. What does that mean? So let's say there's some theta that we're considering, let's say theta equals 1.5. Now, if we flash back to our previous page here for a moment, then there's going to be some initial state. That theta of 1.5 is going to lead to some action that we're going to take next. Then that action we take next and the state that we were just in is going to determine our reward and also determine the state we're in next, which is going to determine the action we take next, and so on and so on and so on. In other words, that theta is going to determine a certain possible trajectory, which is the set of all these states, actions, and rewards that we could go down. Now, because there's some stochasticity built into this process, for example, we're modeling the probability of picking an action. So if that probability is 0.7, at the end of the day, we still need to flip this biased coin, who has a probability of 0.7 coming up more and 0.3 coming up with the action of less. And so that trajectory will be different every single time. So there's all these possible infinite different trajectories we could go down. And so this average is exactly the expected total reward over all of those different possible states of the world, all those different possible trajectories that we go down. Some of those trajectories, for example, just by pure chance alone, are going to lead us down ordering more of the product several times. Other trajectories by different random chance are going to lead to us ordering less of the product, and so on and so on. But what we really care about is, on average, if we were to pick this theta as our parameter, as our policy, what is the expected total reward? And so, falling back on the way we solve these supervised learning problems, if we can find the derivative of this j, the derivative of this expected total reward, with respect to the parameters which define our policy, in this case just theta, then we can use a simple gradient ascent method in order to figure out the ideal parameter theta. Because once you have this derivative, if we're able to find this key derivative right here, then we're basically able to update our theta in the direction of increasing gradient, and in that way use this basic hill climbing approach to find at least a local optimum of this theta. And that, folks, at this point in the video, is exactly what policy gradient methods are. We've defined everything we need to know to understand what those three words means. It's a policy gradient method because we are taking the gradient of this expected reward, which is parameterized by this policy parameter that we set up, or parameters in the more general case. And if we're able to do that, then we can use this method to figure out the ideal policy. We're going to learn this policy in the same way that we would learn the parameters for a supervised machine learning model problem, even though here we don't have labels, and instead we're going to take this expectation over all possible trajectories that this policy could generate. And so now we switch gears to basically saying, how am I going to figure out this derivative of this expected reward with respect to my policy parameters theta? How am I going to do that? And so now we enter a very mathy territory. And so if you want, you can skip forward to the section afterward, but if you are along for the ride and want to understand the math, then let's go. So we're going to be taking the derivative of this j with respect to theta, which is the derivative with respect to theta of this expected reward thing. So this total reward, I've just given a short name of uppercase R. That's going to be the total reward over all possible trajectories. So let's expand this expected value into using the definition of what an expected value is. We have the derivative still hanging out on the outside. An expected value, as we said before, is basically a glorified sum over all possible trajectories tau. And inside we have two terms. We have the total reward that would come from that trajectory, R of tau, and we have the probability of that trajectory under this parameter theta. So this term, let's take a second to understand it. This pi sub theta of tau is the probability that if we did use a policy that was parameterized by this theta, for example, again, theta could be 1.5 or negative 10, something like that, then those are going to lead to very different probabilities that we're even going to generate this trajectory in the first place. Some trajectories are more likely given certain settings of this policy versus other settings of this policy. So far we're here basically appealing to the definition of an expected value. And now we're ready to state this fundamental theorem of reinforcement learning called the policy gradient theorem. Now there's a lot of math that would go into fully proving this, and so I'm going to take kind of a halfway approach between fully proving this for you, which would take a really long time and may not be very enlightening, and not giving you any indication of where this is coming from at all. I'm going to take a middle approach between those things. And so the way we'll start that is basically first just stating the policy gradient theorem, which is the first line on this page. And so again, let me flash back to what we were just looking at before, the definition of this expected value. The policy gradient theorem says that that is equal to the sum over all these trajectories tau times the probability that we would have this trajectory tau under this policy theta, times the derivative, which has now been brought inside the sum, the log of the same probability that's on the outside, times the total reward that we would get from this trajectory tau. Now, whoa, there's a lot going on. Why is there a log in here? Why are we seeing this pi appear twice? It seems like a pretty big logical jump to get from the previous equation to this equation. And granted, it definitely is, and that's where that full proof would really enlighten how we got there. But instead, to bridge that gap a little bit, I want to do two things. First, I want to take these two terms here, which are probably ones you have the most questions about how we got there, and simplify them a little bit. And the other thing I want to do is talk about why we introduced this log here in the first place, even though we didn't technically have to. It's going to make things a lot simpler, especially when we remember that dependency graph we were creating on the first page between what things depend on other things in terms of the states, the actions, and the rewards in our reinforcement learning problem. So first things first, if I take this bracketed term here and I reproduce it below, right here, then we can actually simplify this a little bit. We can say, what's the derivative with respect to theta of this log of pi theta of tau? Well, appealing to the definition of the derivative of log of something, then that's going to be 1 over the argument of that logarithm, which in this case is pi theta of tau, times the derivative of the argument of that logarithm, which is pi theta of tau. Now, you're seeing pi theta tau here in the numerator, pi theta tau in the denominator, so these guys can get canceled. And so this whole thing, we can actually simplify to just the derivative with respect to theta of pi theta of tau. And so if you plug that derivative in for this bracketed term here, you can see how that looks very, very close to this form that we were looking at here. That essentially would be taking the derivative on the inside, which we're allowed to do for sums, And it basically looks identical. The only small caveat, which I have to point out because otherwise it would bother me to not tell you this derivative is technically applied to both of these terms. And if you think about it for a moment, both of these terms do depend on theta. The pi theta of t explicitly depends on theta, but this total rewards of this trajectory also depends on theta implicitly. You can show that for yourself, but we would technically need to use the product rule here and work out a much longer equation. And we can't simply just say, oh, I can just plug that in here and that's equal to the exact same thing. It does require a little bit more work, but you can see the spirit of why the previous equation we were looking at does simplify kind of down to this current equation we're looking at. But that does beg another question. Maybe that does help you make that logical connection, but it does beg the question, why are we introducing this log thing at all here if we're able to simplify it to something much, much simpler? Well, the beauty of this log piece is exactly understandable when we think about what things depend on what other things and how we're able to actually simplify this derivative of this log probability of observing this trajectory under this policy if we now expand what it means to calculate the probability of this trajectory given this policy theta. And we can do that using this rather long-looking formula, but we're going to see that things are going to simplify beautifully in just a second. What is the probability of a trajectory? Well, if I go back a couple pages here, we can basically just work through the trajectory step by step as we did verbally back here. The first thing that happens is there's some probability of the initial state S0. It doesn't really depend on anything, it's just hanging out right there. Then there's a couple arrows here we can put into this product, this large pi notation here. For each time step, the action you're taking depends only on the state at that time step. So I called this out a couple times, and here's where that's coming to fruition. Basically, the action in the first time step only depends on the state in the first time step. The action in the second time step only depends on the state in the second time step. And that's exactly the terms you're seeing right here. It's this probability of taking a certain action given the state in that time step. And the last thing we're missing here is basically the probability of the reward in a certain time step and the state in a certain time step. And those are going to be probabilities, those are going to be functions of the state and action in the previous time step, which is exactly the term that you're seeing right here. And so even though this looks a little bit cumbersome, it's basically just saying in mathematics what we said in words a couple minutes ago. Now here's where the beauty of that log comes in and why it is necessary and helpful to simplify all this. If we were taking the derivative of this pi directly, which is what we could do technically, it's going to be very, very difficult. Taking the derivative of a bunch of things all producted together is going to be a very ugly product rule kind of mess. And so we do a trick that we often do in these situations, where we appeal to the log of a product, and as we know from the rules of logarithms, that's going to decompose into the sum of logs. So here we have the log of the probability of the starting state, plus this product notation becomes a sum notation, and we put a log on the inside. This product notation becomes its own sum notation, and we put a log on the inside on that probability. Now things are about to get really, really awesome, because now we take the derivative with respect to the log, as we see right there. We're going to take the derivative with respect to the log of this pi theta of tau. That's going to be the derivative with respect to theta of all of these terms here. And here is where some beautiful simplification happens, when we think about which of these things actually depend on your policy parameters theta. This initial state doesn't depend on anything, and so this derivative is going to be equal to 0. That's awesome as a simplification. What about this term here? Does the probability of your action in a certain time step, given the state, depend on your policy parameter theta? Literally yes, by definition yes. This probability literally is your policy, being modeled by that logistic regression, being modeled by that sigmoid, and so of course this is going to depend on your policy parameter. What about this guy right here? Possibly the most complicated looking probability in the entire bunch. This is the probability. Given you've already chosen to do some action in this time step, given that there's some state that you're looking at in this time step, what's the probability of a certain state in the next time step and the reward in the next time step? Does that depend on your policy? Well, no, because you've already chosen your action. And by doing so, you've already removed the dependency on your policy. So here's the beautiful thing, and this is worth calling out, this is worth noting. There is no dependency of this very complicated probability term on your policy parameter theta itself. So all of these terms are going to be equal to 0, and we don't need to care about them at all. Why is it important? Why is it significant that we don't need to care about them? Well, for one, it makes the computation easier, but if we think about what these terms would have represented had we had to care about them, we would have had to model the environment. If we did need to consider these terms, we would have needed to have some kind of probabilistic model of given an action and given a state we were in, here's the probability that the environment would be in a certain state in the next time period. And the environment in a reinforcement learning problem is notoriously difficult to model. You think about even a little bit more complicated of a problem. For example, if you're building a stock trading reinforcement learning bot and you're trying to model the state of all of the stock tickers in the next time period, that's going to be virtually impossible. And so it is an awesome property, and really what makes these policy gradient methods powerful and usable in the real world is that they are model-free. There's no need to model the environment, and all this reduces to is basically just the sum over all these time periods in the trajectory of the derivative with respect to our policy parameters of just the term that pertains to our policy. And so to recap, if we want to find the derivative of this expected reward function j with respect to our policy parameters, then that's going to be, by the policy gradient theorem, by this fundamental theorem in reinforcement learning, that's going to be this pi theta of tau, which we're seeing right there, this r of tau, which is the total reward given this trajectory, which is hanging out right there, and now we're able to finally substitute this derivative with respect to the log of this pi theta of tau as this formula right here, which is coming from this derivation that we just did. Now we can actually encapsulate this as the expected value, given some policy parameter theta, of the total reward times that same term we just looked at. Now, why are we able to do this? Because again, appealing to the definition of expected value, this time just going in reverse, rather than expanding the definition, we're appealing to the definition here to write this expected value. This term right here is just the probability of a trajectory, and this rest of this term here is just some measure of that trajectory, and so we put the measure on the inside and we're able to wrap the entire thing in an expected value, just like this. Phew! Well, this video got a lot more mathematical than I thought, but I don't think that's necessarily a bad thing, given this channel is called Freepik Math, and we should flex our mathematical muscles from time to time, especially if it helps us understand the underlying mechanics of the methods that we're using in machine learning, in this case reinforcement learning. And so the punchline, if you wanted to boil this whole video down into one punchline, is that if we want to use these policy gradient methods, which require us to calculate the derivative of this expected reward with respect to our policy parameters theta, all we really need to do, if we look at this final statement down here, all we really need to do is calculate the gradient with respect to our policy parameters of the log of the probability of taking a certain action given the state of the environment. And that is much more tractable to do than if we were asked to just take the derivative of this expected reward function with respect to theta. Going through all this math helps us understand what it exactly is that we need to calculate in order to apply these policy gradient methods in the real world and actually learn meaningful things in reinforcement learning. And so, for our case, we simply just need to take the log of this sigmoid and take the derivative of that log sigmoid function with respect to theta, which is a very easy thing to do. I've skipped the exact derivation here, but it's basically just 2 lines of calculus, and all that derivative reduces to, based on those couple lines of calculus, is that P, which is the growth in demand of this product from one day to the next in this current state, times the probability that under this policy, I would want less of this product in the next time period. And so that's all that is, a very easy multiplication, a very easy product to carry out, which makes this whole method tractable for solving this problem. And that's it, folks. Again, a very mathematical video for you today, but hopefully what you took away from this video is that there is a family of methods called policy gradient methods in reinforcement learning, which are very popularly used from solving simple problems like this to being the last step of telling ChatGPT whether or not the responses it's generating are any good. That itself is a special case of a policy gradient method called proximal policy optimization, or PPO, which we'll cover in a future video. But that's based on this same theory that basically says that if I want my agent, in this case, this handsome little agent right here, to learn a optimal policy to solve some kind of reinforcement learning problem, then it suffices to take the derivative of the expected reward with respect to the parameters which define my policy, those theta parameters, in this case there is just one of them, but in real life there'll be tons of them probably. If you're using something like a neural network to determine your probability, for example, it suffices to take the derivative of that expected reward function with respect to those parameters theta. And doing so reduces to basically just having to take the derivative of the log of your policy with respect to theta. And if we can do that, then we can basically use gradient ascent to learn those parameters theta. And that is what's called policy gradient methods in reinforcement learning. And it's all thanks to this fundamental theorem of reinforcement learning called the policy gradient theorem, which hopefully, even though we didn't prove, gave a bit of the flavor of why this might be true. So, thanks so much for watching. I know it was a bit of a longer mathematical video for you today, but if you learned something, if you enjoyed this video, please leave a comment below, leave a like on this video. It really, really does help. And I will catch all you wonderful people next time.